The code to implement the velocity relay algorithm for the simple harmonic motions could be found in these lecture notes in the IPython format. So here is the code. So once you click on this code, you'll be able to simulate how the particles would be simulated. That is, you will be able to see how the particles position changes with time. So here we are simulating the particles for I think 2 period of time, 3 period of time. That is 3 period. You oscillate from here. Um, go through one oscillation, two oscillation, and three oscillation. And according to what you have learned from the previous study in your um, first year or basic mechanic course, it is understood that the velocity is actually fastest when it passes through the equivalent position, and it will stop temporarily at the end point. Then it will just change its motions, directions, and then we keep on oscillating. So the velocity of the oscillator would vary with time, and then this is the visualizations of the simulation. So let us try to reproduce this code here one by one. Uh, so first of all, you have to decide on the initial condition. So you have to first write or initialize your code. So you need to understand what are the information that is required. First of all, the system is described by the strength of the spring and the mass, and you have to supply the displacement position initially and also the initial condition for the velocity. So these are the first four things that you have to prepare. So the first thing you have to write down for your simulation code is that you do the initialization. So this is called the initialization. Initialization. So here we set the constant k, which is the constant of a spring, and for easy reference, we always set it to 1. You can set the mass to be equals to 1. Once the k and m for the system is set, then you define the omega, which is equals to the square root. Right? The square root is given as np.sq. So here I'm going to import numpy as np. Then NP pi is the pi, and the omega is defined to be, sorry, it's not NP pi, is equals to square root of k over m. So this describes the constants of the angular frequency. Once the frequency is defined, then the period is also then defined to be based on this very simple formula. That is, the t is 2 pi over omega. So we're going to define our omega 2 pi over omega. So here is 2 times pi over omega. So once these three are defined, then we have to set up our time grid. So the grid point for the time grid is to be expressed as in unit of the period. So let us define t last. So t last would be the last time when the length of the time for simulation. So we express it, for example, say equals to 3 period. After you decided already the length of your simulation time in unit of the period, then we have to generate um, the time grid. So the time grid could be generated in many ways. So you have to, for example, you have the options of expressing your time array as, say, uh, lean space, NP lean space, and then you begin from 0 up to t last, and then you want to have, say, for example, NT grid point in the time array of TARR. So here the T could be taken to be just, say, for example, say 100. Okay, so this is one way of doing your simulation. So if this is the case, then that is what we have. So let's execute this and then try to figure out what is the TARR. So the TRR is just a number start from 0 up to the last time 18.8 is referring to T last, and there is a 100 grid point between them. Then you need to know also the delta T. Okay, so the delta T is the difference of the time between the two grid points. So the delta T is actually the difference in time at t0 and at t1. Right? So the difference between the time for, say, for example, this number and this number is defining the t. All the values of this minus the values of this can also be taken as the grid time. So if you don't understand what I mean, it's like this: you have the grid line that you generate. So this is your TARR. You start off from 0 and then you end with T last, and then you have so many numbers of grid point. Then each of these grid point is delta t, right? The delta t is just the difference of t at t plus 1 minus t at 1. So for example, if you choose this point t1 and t0, then the difference between t1 and t0 will give you the delta t. Or you can take any difference between this grid point and this grid point. The difference between these two will always be then your delta t. So you can do that and you define your delta t to be just the TARR of number 1, right? So if you write that delta t, then you have this number delta t. You can try to print out the delta t, delta t. Then the delta t is just this number 0.19, and this 0.19 and this number TARR, these are the same, right? So here this number is your delta t, which is just equals to the first member in the TARR, which is this one. Okay, so that's how easily you can define your delta t. So the numbers or the values of delta t then strongly depend on the numbers of grid point from t0 to t last. So that's how we define the delta t. You need this delta t because it is required in your Valais algorithm. So in your Valais algorithm, we need this delta t. Yeah, okay, this is the one that we need. Okay, so once we have defined this initialization, then we also need to define the grid point, or not grid point, the size of the simulation box. So the simulation box would be this. So you expect that when the simple harmonic oscillator is executed, then the particles will begin from somewhere here at x equals to 0, and then you will oscillate to the right and oscillate to the left at a amplitude of a, right? So we have to define what is the amplitude of a. Then the grid point, so the simulation box would then be starting from f, I think we call it f left and f right. And the height of this is called y low, and we call this y high. So these values of the coordinate is described by x and y, and the y is always set at the length at the height of 0, but the x is going to execute an simple harmonic motion and constantly changing from f left to f right, and the amplitude is just a. So the next thing we want to define in our code is the amplitude. Okay, so here I'll call the amplitude of a. So let us set it to some number. Okay, let me set it to 1, just for simplicity's sake. So that would define the length. Then I'm going to set my x low. Well, I'll call it x left. F left is minus a, F right would be then plus a. So this refers to the leftmost locations of the x grid, and x right, this is x right, to be the rightmost location of my grid. And then the x low, y high would be also defined similarly. So I just need to assign the values of my y low and y high. I'll call this y low, I just call it equals to 1, and then y high, I just call it to be 1. So the exact values of y low, y high is not really that matter. The y low, y high just determine the height of my simulation box, which is this one. Okay, since the particles is not going to move along the y direction, therefore we just need a small a height of y. Okay, so anyway, this will be the box size of my simulation box. If these numbers are not suitable, we can always adjust it later. So that is the initialization. Not yet. We have to also initiate the locations of the particles at t equals to 0. In order to do that, before we continue to write down the code, we have to ask ourselves what are we going to calculate. Here, the important thing to calculate is the instantaneous location of the particle, which is the x, and also the x dot, which would appear in the Valais algorithm. So we need to calculate x, we need to calculate x dot. So x and x dot are two different quantity, and also we need to calculate the ax. So in the simulations of Valais algorithm, usually we require three sort of like variable, that is um, that is accelerations, the locations variable, and also the velocity variable. So these are the three most important variables that has to go into the Python code. In order to calculate the x dot and ax, we have to resort to a new type of quantity that we call this the data type. I think I haven't talked about the data type here. So here the data type we are going to apply is what we call a dictionary. A dictionary is a very important class of data type, dictionary. It allows you to do a lot of things. So specifically, we want to assign the variable as in the form of a dictionary. So a dictionary, it has actually looks like this. It has a name. So here the name of the dictionary, we call it X, and also a dictionary would contain an argument here. So here in this case, the arguments that goes into a dictionary is known as the key, and then the values of the X is called the value. So the dictionary is actually quite easily understood if I give you some simple example. Say for example, you define an X as an dictionary. So you have to first declare that the X variable is a dictionary by setting it to be equals to an curly bracket. This will initialize the X as an empty dictionary. Then you can continue, then you can add content to the dictionary. For example, let's say if you want to um, assign the values of x at time t equals to 0 to be equals to say a number of say 1, and x at the n equals to 1 is equals to 2, x equals to 3 equals to, like for example, 9. Okay, so this is a very simple example of assigning value to the dictionary x. So here 0, 1, 2 are what we call the keys to the dictionary. X here refers to the name of the dictionary. X is a symbol for the dictionary. And the values of 1 through 9 refers to the value of this dictionary. So the example that I'm going to show you is quite straightforward. So let's say, so I'll show you how you declare actually an dictionary. So once you declare x equals to an empty dictionary, then you will say this x with a square bracket, assign it with an key of 0 is equals to 1. So that's how you assign the values of 1 to the dictionary x with the value for this dictionary as 0. You can also try to assign, say, value of equals to 2 at the key equals to 1. And then you can try to, say, declare x with the value and with the key equals to 2 as equals to, say, 9. Okay, so these are three very simple examples. Now, once you have done that, then you can try to print out the values of the dictionary X. So the dictionary X here is like this. It says this is referring to X0, this is referring to X1, this is referring to X2. So how you read this? This is the values of X1 is the values of X when the values is 0. X, the dictionary, has the values of 2 when the key is equals to 1, and values of x is 9 when the key to x is 2. So for example, you said this: print the values of the dictionary x when the key is equals to 2. So that will give you a values of 9. Okay, so if you print x with the key equals to 0, then the dictionary of x will give you the value of 1. Okay, so once you have declared the values of x, you can print out the information about the values by just saying x dot values. Then it will give you all the values in the form of a list. So this refers to the values of x 1 to 9. If you want to know what are the keys, then you just say x dot key. Then you print out 1, 2, 3. So 1, 2, 3 is the keys to the dictionary X, and then these are the values of the dictionary X. So we are going to make use of a dictionary to what I call to contain the information of the locations of the particle X at any instance of time, and we are going to use x dot as a dictionary to retain or contain the information of the velocity of the particles at time, and also we're going to use a x as a dictionary that contain the information of the accelerations in the Rayleigh algorithm. Okay, so that is what we are going to do now. After we have introduced what is the dictionary, then we're going to use it. So we have to assign the initial conditions and also the initial condition for the velocity. And in order to do that, we have to first declare the a blank dictionary x dot and also ax. So this is a declarations for the dictionary x dot and ax. You cannot assign a dictionary without declaring in declaring the variable x is an dictionary. Now let me explain what I meant by that. So let me clean off the memory and let me show you this. So if I want to assign x as a dictionary, if I say like this, it would not work, because when I print out when I write x0 equals to 1, I'm telling the Python that I'm going to create a dictionary called x, and I'm going to assign values of 1 to the x dictionary when with the key equals to 0. So this is not going to work because it says here x, which is the variable name to the dictionary, is not yet defined. In order to make this work, you have to first declare that X is an empty dictionary. Then it will work. Okay, so after that, then it doesn't complain anymore, and you can print out the values of X at 0, and then you will print out the value. Right. Therefore, it is important to initialize the dictionary of the variable X, X dot and AXX. Once these three dictionary is declared, then we assign the values of the initial positions to the simple harmonic oscillator as x0. Here 0, as I mentioned, it will be referred to the key that denotes the time in terms of an integer. X is equals to the values of a when n is equals to 0. Here n is a variable that I'm going to create later on that describes the time. So n will be related to the time. You'll see that later. So that is the initial conditions, and the velocity x dot at 0 will also be assigned a values of 0. So I think that is what is required at the moment. And then probably you have to assign the values of the accelerations ax at 0 and it's equal to some number. So maybe I'll declare this later on as time as we continue to write this code. So I up to this point, we have almost done with the initializations of the code, and it doesn't seem to make any complaint. Okay, so the next thing we want to do is to then try to code these three line of Boolean algorithm one by one. So we have to write this in a for loop and let the t to run from the beginning of t equals to 0 up to the last, which is t last. But you can't write the for loop in terms of t, but you have to write in terms of TARR. Okay, sorry, I think it's not really TARR. So if you write like TARR, then you'll be defining your t in TARR, but then it would difficult for me to assign the values of xn. So there's these complications, okay, that I try to explain here. That is, when you try to describe the positions of the particles as a function of time, this is what you expect, right? So when time changes, your x changes. However, for the velocity algorithm, it has to be actually calculated based on not time, but based on a discrete numbers of n. So this is what I meant. So instead of writing x as xt, we have to write x as n, where n and t are related such that the t of n is equal to n times delta t. So the values of t should be then described in terms of n. But if you were to do this here, then we have some trouble because we have not declared what is the n. So I have to declare an variable tn for the time. So this seems to be not a very suitable way to declare my TARR. So I'm going to write it here as NARR. NARR is the time namespace, which is going to start from 0 up to the last n. So how many n are there? Is that NT? It's yes, it start from 0 up to NT with 1. I think that is what should be. So here TRR is the linspace with the delta t to be just equals to the DARR1, which I have already explained earlier on. Here I define NARR, which is the n array, begin from 0 up to NT at an interval of 1. So TARR is like this. Okay, so I have to make sure what is the numbers of TARR. So here number of TARR is 100. If you ask what is the numbers of item inside the array of NARR, not NARR, here I call this NARR, yeah, length of NARR. Length of NARR is not correct. It should be 100, but here I have only one. So let me look at my linspace 0 to NT 100. So let me check again. So this is my NARR. Then the numbers of NARR is only one. So something is not right here. NARR, so it's only a number. Linspace from 0 to 1 at an intervals of 1. So let me see what is that. NT is 100. So start from 0 to 100 and it's only, I think it should be NT. Okay, so now I'm correct. So the linspace should be from 0 to NT and it has 1 NT. But so I think it's not suitable to use linspace since we are going to generate array of n starting from 0 up to the last NT. I think what is necessary is just equals to range. I think the range would be just sufficient. The range from 0 up to NT. I think that is required. I think that is the same. Okay. So here NARR is defined as 0 to 100. Okay. So that is what we need to describe the NARR. Okay, so let me continue from here. Now, once I have defined my NARR, then I'll begin to write and for loop. For n in NARR, then I'm going to write my t, which is equal to n times delta t. Okay, so these values of t should coincide with the values of t generated in TARR. Okay, so then when n start to change from 0 to 1 to 2, so is the t will also to increase. Okay, but later on we show that this is actually not really required. We only required n. Okay, so once we have done that, then we can start to write the code for the first line, which is the calculations of x in the next line. Here we said we are going to calculate the values of x at n plus 1. So this is going to calculate the values of x at n plus 1. So initially n is beginning at 0. Right? So NARR start with 0. So when n is 0, then this is referring to 1. So the locations of the particles at the time t equals to 1 is equal to the values of the x at the previous time step, which is the time step at n. Right? So this is the next time step, n plus 1, n is the previous time step. So the values of the next time step is the numbers of the previous time step plus the product of the x dot at the previous time step. So here x dot refer to the velocity. Okay, if you look at this code here, x dot here is actually the Vx. The Vx and the V dot is understood to be referring to the same quantity. So here sometimes I use x dot, sometimes I use v, but when you see a x dot, it means that it is a time derivative of x. It is necessarily understood to be also the velocity of the particles along the x direction. Then this is the product of the velocity multiplied with delta t. Delta t, and then you add it with the 0.5 multiplied with the acceleration a x at the time n multiplied with delta t squared. I think that is what is required here. Half ax at the previous step multiplied with delta t squared. So here the ax is the accelerations of the x coordinate at the previous time step, which is an. And what is this an? We have to define the x of an before it is called, right? So this value of x at n plus 1 will not be able to calculate if you do not have the Python what is ax in the previous slide. So we have to define the ax at n here before it goes to the next line. Okay, so what is ax? Ax is the accelerations of the particles um, at the time n, and the acceleration actually is not dependent on time, but it depends only on the position, right? So the ax is calculated once you know what is the locations of the x. So here we are talking about ax at the time n. Therefore, this is equals to the values of ax calculated when x is at the time n. So that is what we are going to write for the ax is equals to minus omega square multiplied with x at n. Okay, so that is how you define the ax and before you go to the next line. Now this line has now been correctly calculated. Let us try to run the code and troubleshoot it in case the code is not working properly. So I execute this one. It's not complaining. Let me execute this one. It seems like it's complaining because I misspelled the delta. So that should be delta t. So I execute it again and it's not complaining. That means at least it is not wrong at this line. The next line we want to write is the line number 2 to calculate the acceleration at the next time step. So here we are calculating the ax at the next time step. The ax at the next time step is simply equals to this, right? It's simply equals to omega square minus omega square times the locations of x at n plus 1. I think that is simply a repetition of the definitions of ax at n. So here instead of instead of t at n, you define the acceleration at the time n plus 1. Then remind you, ax equals to omega square x is actually the equation of motion that we begin with in the beginning. Like I mentioned to you earlier on, the equation of motion for the simple harmonic motion is expressing the acceleration in terms of some function of x. So here it so happen that the equation of motion is acceleration equals to just omega square x. So you can always calculate the accelerations from the equation of motion. So once we have calculated the acceleration at the next time step, then we calculate the x dot, which is the accelerations of the which is the velocity of the particle at the next time step. So here we refer to number 3. The accelerations of the third time step is just equals, so not the acceleration, the velocity of the next step is just simply equals to the velocity at the previous time step plus the average of the accelerations at time step before and after. Average here means that you sum up this one divided by half and multiply with the delta t. So you write this code as x dot at time n plus 0.5 multiplied with the values of ax at n plus ax at n plus 1. And don't forget, you also have to multiply this with delta t. And yeah, so that is what is required, delta t. So we let it run and it's not complaining. So it means that I have able to iterate the values of ax, an, ax, and x dot for all the n that is spanning all the time grid. So it means that the values of xn here is changing from one time step to the next time step. So you can try to print out the locations of the xn for all the time step and simulate it. So what you do is that remember what we do it in order to do the display, just say for display and display. So that is how you do it. So I said um, display. I need to import the display function from Python import display, and also I need to import the numpy and also the matplotlib. So here I already imported my numpy, so here I just only required to import my matplotlib and the display from IPython. So these are the packages that is required to perform an simulation. So here I call out the display and clean the grid or the simulation box, then display and then show the plot. Okay, so here I'm going to show the plot, plt.plot, plotting the point of x and y. So here is x plus 1, and so I think x of 0, and also y at 0. Okay, so here this is referring to y at 0. So you can say this to be y, and your y is permanently set to be at the values of 0. Okay, so this is one way of doing it. And then when you plot it, when you plot a point, so we do a point, which we do a plot point. So this is how you do a plot point. So you plot the coordinate of x and y for the oscillator, and this is just a point. I think that is more or less done, but there's one more thing to do. That is, you have to fix the x-axis and the height, well, the length of your simulation box. You have to fix it. So you have to do one more thing. That is, you have to plot x limit, and your x limit has to be from minus x left and x right. So these are the number that I already declared earlier on, f left and x right. So one that's done, what else do I have to do? And probably I want to also plot another point. So I'm going to plot another point on the same plot, that is to show the point of 0, 0. So this is a point of x0. This is origin, and I'm going to put an x mark for the origin. Then I'll run it and see whether it works. So now I have a simulation that doesn't work. That is because I have not included what I call plot show. So you have to ask the Python to display the current state of the plot plt. Once it's shown this one, it would you will be able to display the simulation. Okay, so that is what I expected to see, but I don't see any change in the simulation. Something is not right here. Okay, let me try to rerun this and then start again, executing this one and then execute this one. Okay, so that is not working very well. Something is not correct. So let me check if my simulation is correct. I should be able to see my x changing like this. So this is the plot of x and y. Okay, so maybe I should do it like this. Not sure whether this is the required change. Okay, so let's try it again. It's not changing. So it's not simulating. NARR should be changing. NARR. So the NARR, no, I think NARR is the one that is giving me problem. So for N in NARR, this is not changing correctly as I expected, because N is supposed to be changing. So I should ask N to be given as an array. So here, this is not quite true. I think an array here, linspace as Yeah, I think this is not correct. For some reason, I didn't change this just now. I forgot. So this should be defined as just an range. Okay, a range from 0 to NT. I think that is the required NARR. It runs from 0 to NT, which is 100. Okay, so I think that is my error. So let me check again, NARR. So NARR should be a range that change. So now the NARR is correct and N is changing. So I hope that when I press the button, this one should correctly execute. Yeah, so it's executing and it's executing as expected and is oscillating. Now to make things look slightly better, I would actually like to add in an AX horizontal line at 0. I think this would uh, show the executions of simple harmonic oscillator about the center 0, 0, and you can see that it's actually moving as expected. It's moving fastest when it passes through the equilibrium position and it stops for a moment and change its directions at the end of the amplitude, and it's executing exactly 3 period of oscillation as I designed it. You can make the simulation to be slightly more refined by improving the resolution in time. So instead of 100, you can try to say improve it to be 500. Then the simulation would be finer, right? So you would not see the change like in the more discrete manner. Here it's like more refined, so you can see the change in the position more refined, but it also takes a smaller, shorter time. So that is a very simple example of executing the simple harmonic motions, simulate the simple harmonic motion using the Valais velocity algorithm.